Hello students, let's begin lesson 10, estimation. In this class, we are going to consider two types of estimations. One, point estimation, which consists of a single point or a single number, and the interval estimation, which is an interval typically centered at the point estimate, give or take, plus or minus. And the point estimation is typically the corresponding sample statistic. For example, if you want to find out or if you want to estimate the mean length of a certain fish in a lake, say rainbow trout in a certain lake, what do? Do you drain the lake and measure everything and let them all die? Certainly not. You're going to take a sample and then measure those lengths of those sample fish and then take the sample mean and use that as a proxy. And that is the point estimation. You can do that, and you can do that reasonably accurately if, number one, if the sample is well represented, no systematic bias. Number two, if it is well randomized. And number three, if it is large enough. You can do the same thing for standard deviations or proportions and so on and so forth. That kind of thing is point estimate. The most important and the easiest for us is the mean, so we're going to focus upon the mean, but we're going to consider other population parameters as well later on. Now, what is the interval estimate? There are several interval estimations, but here at this level, we're going to do only confidence intervals. There are other interval estimations too, prediction intervals, tolerance intervals, and things like those, but those are for upper level stat courses. And prediction intervals for 3000 level and tolerance interval probably even higher. In this course, we do only confidence intervals. All right, I mentioned confidence interval several times. What is it? Well, I can give you some explanation like that, but it's difficult to understand without the picture. So please pay attention to the picture. We begin with a point estimate, and then we consider the margin of error, minus the margin of error, plus the margin of error, and then form an interval. All right, so we have confidence interval, typically the point estimate minus margin of error, margin and then point estimate plus margin of error. It looks kind of like this. Here I use bracket as if it's always closed interval that we're interested in, but if you use parentheses, that's fine too. So basically, the center point minus something plus something and form an interval, which is highlighted in blue. Now, what is the so-called margin of error? One aspect of the margin of error is that it's the radius. It is centered at point estimate plus the margin of error to get one side minus margin of error to get to the other side. So it's the radius, half of the diameter. Another aspect is this. Is the maximum error is the maximum error within the confidence interval. What do you mean by that? Let's suppose the real population mean belongs to this blue interval. And the distance or the error will be the distance between x bar and mu, which we don't know. It exists somewhere, but we don't know exactly where it is. But if it is inside this blue interval, then it's not going to exceed the radius. If it goes farther out, then it doesn't belong to the confidence interval. It's out, so it's out of bound. We don't consider that. So that kind of summarizes the concept of margin of error. All right? If my interval estimation is done right, then the real population parameter, in this case population mean, will belong to the interval somewhere. It's going to be inside this blue interval somewhere. If so, then the error will have to be less than this margin of error. So the worst that can happen is right at the endpoint or at the other endpoint. If you get further, then it goes out of that confidence interval, our interval estimate. So our interval estimation actually failed. So assuming our interval estimation worked, the margin of error is the maximum error within that. So it has many aspects. Now, another concept that you have to remember is the confidence level. What is it? Let's see. Nothing is absolutely certain in statistics. I'm doing this interval estimation. I may do it right, or maybe I'm wrong. Okay, what's the chance that my interval estimation turns out to be correct? That's basically what this confidence interval is talking about. It's the probability it's basically the probability that my interval estimation is done right. In other words, it's the probability that the population parameter indeed belongs to the confidence interval. Indeed belongs to the interval. So my best point estimate is the sample mean, and then assuming my sample is well represented and well randomized and large enough, it is quite likely, more likely than not, that the real population mean is close nearby. Consequently, we have higher probability density around the best point estimate, x bar, the population mean. And then there's relatively little chance or smaller population density, probability density, that the population mean will fall. So the population mean, mu, is likely to be closer to x bar than far away. Of course, we know nothing accurately. Nothing is certain in statistics, so everything is by chance. So by some bad luck, this entire sample is pretty low, and then real population may be much higher over there. It's possible, it's just that kind of chance is pretty low. Now, how low and how high, that's measured by confidence level. This picture visualizes the 95% confidence interval, which means the blue region here is 95%. All right, the blue region here is 95%. That means there's 95% of chance that the population mean belongs to this blue interval at current stage. Now let's adjust this. What if I want more confidence? Let's go 98%. I would like to be a little more certain that my interval estimation is correct. So I'd like to be 98% certain that the real population mean comes within my confidence interval. What do you think will happen? Bigger interval, so that, bigger area there. Now, the probability here is 98%. There's 98% chance that real population mean fall within this interval estimation. If I go 99%, even more. So, more confidence, which means this interval estimation is correct, and that chance is 99%. So, more confidence, that's good. But then again, it comes with a trade-off. If my interval estimation is correct, then how about the error? I have much bigger margin of error now. So even if my interval estimation is correct, within that confidence interval, I have big error to work with. Who likes big error? Nobody. So let's go down. Let's reduce back to the default of 95%, and let's go down to 90%. So this area is now 90%. And then let's go down even further, down to 80% now. So I have much smaller margin of error. That means, assuming my interval estimation is done right, the population mean will fall in this blue interval within my interval estimate, and the margin of error is much smaller, so the error is actually much smaller than that. So smaller error, that's great. But then again, small error under the assumption that the interval estimation is correct. But then again, I only have 80% of chance that this interval estimation is correct. The other 20%, it'll fail. 10% toward this way, 10% toward that way. So I only have 80% of chance that this whole thing is any meaningful. That's not good. Nobody likes lower confidence. Let's go back to where it was 95%. And balancing this is actually a tricky business. So more confidence level, that means bigger chance that my interval estimation is meaningful. But then again, even if it is right, I have large margin of error to deal with within that interval. Now, if I not reduce that margin of error within my confidence interval, then I'll have to sacrifice the confidence level, and there's some good chance that this entire thing is meaningless. Is there any way to improve both? Yes, there is. It turns out that margin of error is z times SE, it turns out, and we are going to talk about why that is the case a little bit later in a separate video. So margin of error is z-score times SE, and that is z-score times sigma over square root of n. And let's see, when sample size is big, then square root of n is big. So the sigma over square root of n will become small. So standard error is small. So multiplying by z, and margin of error will become small. So even with big confidence level, I can reduce the margin of error by taking large sample. Great, but then again, that too has its own trade-off. Large sample size means more bigger survey, more people to interview, more fish to catch, and then keep all those randomness and stuff, which means much bigger budget. So still, there are trade-offs one way or the other. You have to somehow balance all that. Of course, those kind of things do not concern me because I'm a mathematician. I'm going to talk about these kind of things based on a certain confidence level or certain margin of error, and so on and so forth. All right, so much for the theory, and we will solidify our understanding through an actual example problem. But then again, that'll have to wait. I'm going to do that in a separate video. Stay tuned.